So we are on the home stretch with Aqueous Equilibria. So there's one more, there's a couple more ideas we got to talk about. All right, so there is a whole class of mixtures using acids and bases which we have not covered yet. And these solutions contain a weak acid and usually its weak conjugate base initially. And so this is called the common ion effect, which means that there are two sources of a species. So let me give you an example. Acetic acid looks like this. You're going to have this methyl group CH3 and then a carboxylic acid, COOH. So this is the structure of acetic acid. Its conjugate base is going to be the acetate ion or the acid portion just with a proton removed, CH3, COO minus. All right, so you've got a weak acid and its conjugate base. All right, so the chemical equilibrium for acetic acid and water would look like this. You have acetic acid plus water. Okay, the water is going to take the proton away from acetic acid, so you're going to form the acetate ion, COO minus, plus H3O plus. Okay, so this is the chemical equilibrium. So what if you start adding in some acetate ion here? Okay, how would you add it in? Well, we could add in sodium acetate, which is really, really easy to come by. Okay, it's part of it's a food preservative, so it's definitely plentiful. All right, so give lots of details, including the change you would see in pH. All right, so this goes back to Le Chatelier's principle, which we talked about like probably a long time ago now. But if we're adding a stress by adding more acetate ion to the solution, what's going to happen? The reaction is going to have to alleviate that stress. And so if you've got a lot more acetate ion, what's going to happen is that this hydronium ion is going to react to form more acetic acid. So the reaction goes towards reactant formation. Okay, so the reaction goes towards reactants, and that means that the concentration of acetic acid will go up, will increase, and that also means that the pH will increase because the H3O plus is being used up. So since there's going to be less H3O plus, that means the solution is going to become more and more basic. So we're noticing that the concentration of H3O plus goes down because you're using it up to make more acetic acid. All right. So that's pretty much what we expect for this to happen. Now I'm going to make a note here because we got a problem coming up that the Ka for acetic acid is going to be 1.8 times 10 to the minus fifth because we're going to need that number. All right, so here's our problem. Calculate concentrations of all species and pH for the following mixture. Okay, so you've got 100 milliliters of 0.1 molar acetic acid. All right, and keep in mind that if you take 0.1 liters, okay, 0.1 liters times 0.1 molar, this is going to be 0.01 moles of the acid. Okay, and then if you do the same thing for the acetate ion, 0.1 times 0.1 should give you 0.01 moles of the base. And the initial pH is going to be around 2.87 if you were to calculate the pH of acetic acid. All right, so we're going to set this up using the equation that we have before. So we're going to use this chemical equilibrium with acetic acid. So let me get that equation out there. So CH3COOH plus water is an equilibrium, and you form acetate ion CH3COO minus and hydronium ion. Okay. All right. So what I'm saying is that initially you have 0.01 moles of acetic acid, you have 0.01 moles of acetate ion, and you have no H3O plus. Okay. Now, if we do the completion moles, Okay. If we do the completion moles here, there's no H3O plus to use up because initially it wasn't there. So the concentration of acetate ion remains unchanged. It's still 0.01 moles. You have no moles of hydronium ion, and the concentration of the number of moles of acetic acid is still unchanged, 0.01 moles. All right, so by adding those 100 plus 100 mils, that's going to give you 200 milliliters total. So if we were to measure the molarity of both of these, 0.01 moles of acetic acid divided by 0.200 liters, that concentration should be 0.05 molar. Same thing for the concentration of the acetate ion, 0.05 molar, and for H3O plus, 0. All right, so at equilibrium, the molarity would be 0.05 minus X for the concentration of acetic acid, 0.05 plus X for acetate ion, and then for H3O plus X. All right, so if we set up our Ka expression, Ka would be equal to the concentration of acetate ion, CH3COO minus, times the concentration of hydronium ion, H3O plus, divided by the concentration of acetic acid, which is going to be CH3COOH. Okay, and this is going to be equal to 1.8 times 10 to the minus fifth. So if we substitute our numbers in, acetate ion was 0.05 plus X, hydronium ion is X, and then acetic acid is going to be 0.05 minus X. This is all equal to 1.8 times 10 to the minus fifth. Some of you might be seeing what's going on. If we apply the approximation over here, the X is not going to change the concentrations of acetate or acetic acid very much. So those concentrations can remain unchanged. So that's 0.05 times X divided by 0.05. Those numbers will cancel out with each other. So X is going to be equal to 1.8 times 10 to the minus fifth. And so that's going to be equal to the concentration of hydronium ion. And if the pH is equal to the negative log of the concentration of H3O plus, the pH is equal to 4.74. Okay. And so if we calculate the concentration of acetic acid, CH3COOH, it would be 0.05 minus X. And so that number should come out to be like something like 0.0499 molar. And then the acetate ion, CH3COO minus, that'll be 0.05 plus X. And so that number is going to be pretty much, it's going to be like 0.051. All right. So where have we seen this kind of a problem before? We've seen this problem at the half neutralized point. All right, so why is this calculation the same? You have equal numbers of acid and base. Okay, and there it is. So, next question. Why? Explain why this is called the common ion effect. In other words, what is common between these? All right, so remember that the acetate ion, CH3COO minus, comes from acetic acid, CH3COOH. All right, so in order to form the acetate ion, you have to form acetic acid and then just deprotonate it. Okay. All right, so you've got that. And then we're adding in CH3COO minus. We're adding in the acetate ion from sodium acetate. Okay. Now, looking at this chart here, you're starting initially with just acetic acid, but as the concentration of H3O plus decreases, as you start adding more sodium acetate increases because the acetate ions shift the dissociation equilibrium to the left. Because again, like we saw with that reaction, you start adding more acetate ion, the reaction has to find a way to balance itself out and make more acetic acid.